Okay, we're going to demonstrate the capabilities of defining a function in a recursive manner. Technique is known as recursion in computer science and is useful for allowing a program to calculate something where the condition of one step is based on the result of a previous step. This is usually a very uh, uh, clear way to define algorithms. When you're writing the algorithm, a lot of times it makes sense to you as the programmer to think of the value of a current step being dependent on the previous step. And we can do that by making self-reference calls. So you can define a function where it can call itself. There are some definite conditions you need to make sure that occur when you define a recursive call. And we'll go through those when we get there. But let's go through a simple recursive function here. This is a recursive definition of a function. So the value of the function is going to equal 1 if we're on the first term, or if we're on the nth term, then the value of the function is the n minus 1 term plus 3. So if we were to think about what this might generate, is this would generate the sequence 1 and then 4 and then 7, because 4 plus 3 is 7, and then the next term would be 10, and then the next term would be 13. Oops, 13, can't type. Next term would be 16. Next term would be 19, 22, 25, and 28. And then it would just keep on going like that. So the value of each term, the term 22, is dependent on the value of 19 plus 3. And 19 is dependent on 16 plus 3, and it goes backwards from there. So if we can define a function such that it is recursive, we can call it with our value that we're interested. So in this case, n equals 10, we would expect a value of 28. And what it would do is it would say the value of 28 is actually the value of the previous step plus 3. And that value of the previous step came from the previous step, which came from the previous step, which came, etc., all the way down the line until we get to 1, where we have a definite definition. So we're going to go ahead and implement that in code. I've created a little Windows form program here where I have a text box where the person's going to enter in the value, the term they want to calculate. They'll hit the calculate button and it will display the result here. So let's go ahead and work on our button click event. This is where we're going to have it display the value of the function. So we'll say that label 1, that's where we're going to get our results. Label1.text is going to equal, now we would need to call the function. Let's call it fn, and I haven't declared that yet, so that'll be an issue with the development environment. And we're going to pass it the value that's in the text box. We'll call that n, capital N, also not defined yet. But this could be very simple, where I could call that function and return a value. So let's go ahead and define some things. Int n, and we'll say that's equal to 1 by default. And the value of n is going to equal the value of the text box that the person entered it in. So we'll convert that to int 32. And we'll take it from text box 1.text. That'll get the value from the user. And it now needs to pass it to the function, and the value of the function will be returned and stored in our label. So now we need to define that function. So we know it's going to return an integer, and we're going to call it fn, and it's expecting an integer, the number of the term that it's going to be calculating. So we have two conditions here. We have the condition where n is equal to 1, so let's go ahead and write that in as a condition. If n is equal to 1, then we know that we need to return the value 1, because that's what it's defined as. That's simple enough. And helps if I don't have a typo there. You'll notice that we get this little undersquiggle there that says, not all code paths return a value. That's true. So if n is not equal to 1, we know that it's something greater than 1. So we want to do something different in that case. So what we're going to do is we're going to return, and actually I'm going to I'm going to make this a little bit more apparent. This is not the way I would write it if I was actually writing the function. This is how I'm going to write it for our demonstration purpose. I'm going to explicitly declare a value here. We'll call it int, and we'll call it uh, intermediate. So intermediate is going to equal the value of the function fn for n minus 1 plus 3. So the current term fn, when it's not equal to 1, it should equal fn of n minus 1 plus 3. So it's going to call itself, you'll see, and then I'm going to return intermediate. Now, I would not normally write this way. What I would normally do is I would simply make that as a single term. I would put it in as return fn of n minus 1 plus 3. That's how I would normally write this, where I would simply return back the value of the function as defined for this value of n. But when we're going through our program and stepping how this thing works, we're going to want to see this intermediate value when we step through it. So I declared it as a specific value, allowing us to see it. So what's going to happen now is I'm going to come in, I'm going to type in my thing, I'm going to click my button, and n is going to take on the value of the information in the text box. Then the text box label is going to take on the value of the function at n. So say n was 3. If n was 3, then we would call the function n with 3. This would take on the value 3. Is 3 equal to 1? No. So intermediate takes on the value of the function called when n is equal to n minus 1. So 3 minus 1 would be 2. So this function would call back to here. So we would go back into here with n equals 2. Is n equal 1? No. So it's going to take on the value of n equals 2 minus 1, which would be 1. So it would call the function back here. N would equal 1 this time, so we would return 1. That 1 would go back to the copy of int of fn when n was equal to 2. And so that value would replace this, and so we'd get 1 plus 3, or 4. So intermediate should take on 4, and we return the value 4. The value 4 comes back to the value of the function when it was n equals 3, so we get 4 plus 3 should be 7, and that gets returned back to the call that made it, which was the original call up here, and we should get an answer of 7 when we watch this code run. So we're going to do this twice. We're going to actually just run it. So if I hit 3 and run it, I get 7. If I hit 10 and run it, I get 28. So those are values that we expected from our chart. You'll see 23, 25, 28. Those are values that are in our list. 25, 28, 7, 4, things like that. So it's working. Now let's go ahead and take a closer look at its operation. So I'm going to put in a stop so that I can walk through this program one step at a time. So I'm going to go ahead and run and put in my value of 3. Calculate, and you'll notice that I now am in my debugger and I'm stopped. So here I see that n is equal to 1 at the moment. So when I execute this step, I'll step into, in this case, because we want to go into subroutines. You'll notice that down here that the value of n is now equal to 3. And I'm going to step into that function call is now I'm into my function n, or fn, and the value is currently 3 for n. And let's go ahead and put in intermediate so we can see the value of that function as well. So I'm going to continue to step into n is not equal to 1, so intermediate takes on the value of the function for n minus 1. N minus 1, you'll notice right here in the debugger, is now got the value 2. So this should actually execute and call function again. And now I've got n equals 2. So I'm going to step into that. Is n equals 1? No. So intermediate takes on the value of the function when n is now equal to 1. So I'm back in the function again. I'm stepping. Is n equal 1? Yes, it does. You'll see it here down here, n equals 1. So that means it should return 1. So we go into this particular portion. It returns 1. And now where does it end up back? It exits my function, and it returns back to the line that called it. The line that called it was this, and now fn of n minus 1 has a value of 1. So 1 plus 3 the computer can now do, and you'll notice that intermediate now has the value of 4, 1 plus 3. And it's now going to return that, and that's going to go back to the line that called it. We're back on that intermediate call that called it, and this function, fn, is now got the value of, sorry, n minus 1. Sorry, the function is going to have the value that was returned from it, which was 4. So 4 plus 3 is now 7. So intermediate returns 7. So intermediate will now return back to what called it, which was the original function call, and the computer will now display our results, n equals 7. You can see how the recursive functionality takes care of the steps for you. Falling back to the previous version allows you to effectively use stack storage, storage of the program state, to keep track of all of your intermediate values for you. Next, I'll post a series of videos that will explain how to implement the binary tree algorithm that we were talking about today. I chose to do this one first because the binary tree algorithm is going to actually use quite a bit of information about classes and things that are not strictly recursion, but it's coming next.